Welcome back, everybody. I think it should be recording. It's recording. Everything is good. So, thank God it's Friday. This is one of those weeks where you just can't wait for the damn thing to end. So I'm today, I think we can move on to starting to talk about carbocations and alkenes. In some ways, the mechanisms are more complicated. In a lot of ways, the mechanisms are going to be simpler for the next bit. It's going to be kind of a mix of them. We're just going to now have to consider the relative stability of carbocations. We're up to this point. We've really been looking at reacting with carbonyls. Yeah, we are bang on schedule. It's terrifying how on schedule this is. I'm wondering if that's because we're losing things, but yeah, we're supposed to be talking today about carbocation formation and the Markovnikov addition of water to alkenes. So we talked last class about some carbocations. Any questions about anything like that? We can start that. I didn't get any by email. Otherwise, we can work through a few questions. Okay, I guess we'll see where this takes us. So let's say I have an alkene. So we're going to see a lot of this. And we're just going to make an intermediate. It's going to be, this is going to make a carbocation. I'll tell you that right now. Okay, so with all of these types of things that we've been looking at, the first question is, what is the reactive thing that's going to be interacting with in the first step? What are we going to work with in the first step of the reaction? Yeah. I'd say, like, it is good job, Faith. Thanks for jumping in, but hopefully you're like, yeah, of course it's H+. It's always H+. And there's no tricks. If there's H+ there, I'm just thinking, I think I can safely say if there's H+ present, it is always involved in the first step. It's just that I think I'm comfortable with that as a rule. And I'm waving my hands around and you're missing the hand waving because of the camera being off. It doesn't really add very much, but I don't know. Maybe it's slightly less isolating. Okay, so that is going to be react, but that doesn't react on its own. So what else do we have in here that can do any kind of chemistry? So a couple ways to think about that. We can look for lone pairs. There's obviously no lone pairs. We've been dealing with lone pairs. There's a plane going by. Yeah, double bond, right? So we don't have any lone pairs, but we have the weakest held electrons. We have the most available electrons. We have the most accessible electrons, and that's in the double bond. And if we remember what a double bond is, we can it's two p orbitals, right? With one electron in each of them. And we can have one electron in each p orbital, or we can have two electrons in one p orbital and have the other one empty, or we can have two electrons in the other p orbital and the other one empty. So then we have a minus and a plus, right? There's a resonance structure. There's two resonance structures we can draw with this double bond, right? We can put the lone pair on one carbon or the lone pair on the other. Are they good resonance structures compared to the double bond? God, no, they're not good resonance structures, right? The carbons are neutral. It's not like a carbonyl where the bond is polarized. The carbon-carbon double bond is pretty much non-polarized. So we've just created charges out of nothing. This isn't great. So they're not massive contributors to the resonance structure hybrid. But of these two structures, which one is more stable and why? Of the two resonance structures. Jesse says red. So you got the which one and now the why part. Yes, okay. Perfect. Faith, Crystal, boom. Yes. There's no tricks here. You guys are going, except I'm going to poke at you because Lauren and Faith, you both said the positive carbon in the red one is secondary. Is that secondary? How many carbons? Yeah, perfect. There we go. Awesome. Tertiary, right? Whereas here the positive charge is secondary. And remember, we want lots of hyperconjugation. So tertiary is better hyperconjugation than secondary, so we want the positive charge on the tertiary carbon. Similarly, equal and opposite, we want the negative charge on the less substituted carbon. And so we have, like, it's almost by definition in this case, right? We have the other way. So it kind of all works together. Here we have the negative charge on a secondary, which is better than having a negative charge on a tertiary. So everything points towards this. Now, remember I was saying that a lot of reactions, a lot of molecules react as if they are their second most stable resonance structure. Well, this is the most stable resonance structure. This is the second most stable resonance structure. Draw the reaction you expect that to have with H+. That second most stable resonance structure. Hopefully this is a really simple question. You're going lone pair, negative charge, H+. Whee! Sound effects aren't necessary. But I always imagine electrons are having a really good time flying around molecules. So we make that. So this is a way to think about it. So we get this is the product, or this is the intermediate, not this. And it's because we have a tertiary carbocation at first, a secondary carbocation, a second. The tertiary is more stable. So we have multiple ways we can think about that. We can think about the way we just did, breaking down the resonance structures. That's a little bit slow. Another way you could draw this entire mechanism completely properly, and probably the preferred way of doing it. It's implying the same thought pattern, but I'm just going to directly use the electrons in the double bond to attack the H+. Now, the one complication of this drawing the mechanism this way is it's not clear where the electrons are kind of pivoting on. Like the electrons are coming from a double bond, so do they make the bond on the top carbon or the bottom carbon? It's not clear from that arrow. It's implied by the way I drew the product, which way that goes. And I know which of these products we draw because the carbocation is more stable there than at the other site. So we get this. Does that make sense? We do not get this. We'll delete the not. So we get the hydrogen at this carbon, not because the hydrogen wants that carbon. It's got nothing to do with what the hydrogen wants. Who gives a shit what the hydrogen wants? It's all about where the carbocation wants to be. The carbocation wants to be on the tertiary. It does not want to be on the secondary. So the hydrogen goes here because the carbocation wants to be there. Again, what we're worrying about is the stability of charges. Like it could be the subtitle for this entire course, right? The stability of charges. Did that help, Amanda? Awesome. Okay, great. So let's do another example. Okay. Try this one out. Draw your arrows. So Amanda said, okay, so if everyone people start drawing this out on paper or tablets or, you know, holograms, whatever, stone tablets, we have a variety of technological implements in this group. So I'm going to go back and answer Amanda's question. So Amanda was saying we want due to hyperconjugation, we want the hydrogen on negative carbon. Well, due to hyperconjugation, this carbon is negative, and so it can attack the hydrogen. So your I question your causality. Because the electrons are going to be more localized on this carbon, because this one is positive, this one's got more electrons. This has kind of got the lone pair, and it can attack the hydrogen. If anyone's got the lone pair, it's that carbon that's got the lone pair. Does that make sense? So why is that intermediate? It's intermediate because it's not a product. It's charged still, right? So if I said, hey, are you done? You go, no, I'm not done, but I haven't told you what to do next. Because we'll get there in a second, but let's just do this stepwise. Yeah. So this one with H+, hopefully people have done this. You've either looked at it and broken it down. And so I'm going to do the less drawy way. So hopefully you got that. Because your choice is to either put the carbocation on a primary carbon or on a secondary carbon. And given that choice, I really hope you put it on the secondary. Does that make sense? Does anyone have a challenge with that? Okay, we're going to come back because none of these are reactions. None of them are done. Like this, this isn't stable, right? These are all intermediates I'm drawing, but I just want to highlight this is the hard part. The next part's really easy. Not the next question, but the next part of what you do here. Okay, so now I'm going to give you a hard question. Yeah, let's put these in square brackets. That is absolutely what we should be doing, Samantha. I'm very happy putting these in square brackets. I think if I was drawing these as part of a full mechanism, I probably would. It's a little bit acceptable, I think, in these cases, because these carbocations are actually existing intermediates. They are stable, they're not stable intermediates, but they're valid Lewis structures. And so it's okay to not put them in a bracket. They are real. Very transient, but real. It is also not wrong to put them in a bracket. I normally make sure I put things in brackets that are not real, where I'm like breaking rules on how many things can be attached to carbons and charges are all over the fucking place. When I see something like that, I make sure I put it in a bracket because I don't want to say that it's real. These ones are real. They exist. They just don't exist for very long. Okay, the example I'm going to give is this one. Next example. Okay. Take some time, draw it out, think about the two options. And consider what possibilities here. I'm obviously trying to trick you, so think carefully about it when you draw it out. I'm telling you I'm tricking you, though. I can basically guarantee there's going to be something like that. Like that, this is going to be the core concept of a question on the final. It always is, because I like it. Okay, so if you're ever faced with something like this and you're not, for whatever reason, you're not sure, it's never wrong to draw both products and compare. So let's do that. I'm not good at left and right, and somebody said the color pointed out because I arbitrarily drew them in different colors, and that actually worked really well for me. So I'm going to do that again here because I might not be good at left and right, but I'm pretty good at purple and red. I really hope there's no one who's colorblind in this audience. I have a colorblind colleague, so we're very careful generally about red-green. Anyways, which of those carbocations is more stable, red or purple? And why? Nora's in for red. And doesn't have an explanation for why. Unless Nora does have an explanation for why. Okay, Braden says tertiary. Okay, so we've got, I see resonance, I see tertiary, oxygen is slightly negative, purple because of hyperconjugation, red because of hyperconjugation, red because of resonance. I think we basically have every single possible answer. Okay, so let's break this down to individual effects. Where is the hyperconjugation effect stronger, in red or purple? Perfect. Great. Awesome. I agree completely. Better hyperconjugation. Okay. So the trap here is that hyperconjugation isn't the only thing to consider. So a lot of you guys are saying resonance. Can anyone who is saying resonance explain what they saw for the resonance? Because resonance is a great answer, but you know, it's a little bit like saying because. Like, because why? Double bond with oxygen. Perfect. So the red one here, which is now getting a line drawn purple, which makes no sense. Has a pretty good resonance structure. So resonance in and of itself isn't always going to beat hyperconjugation. What's going to cream hyperconjugation, though, is everyone having their full octet, right? And in the second red structure I've drawn up there with the positive charge on oxygen, all atoms have their full octet, whereas for the purple one, that's not the case. All atoms do not have their full octet. I am never going to give an example in this class where hyperconjugation beats resonance. There's a single example where that is the case. The only time that resonance is not as strong as hyperconjugation is the allyl cation versus a tertiary cation. This has resonance, but the resonance is between two sucky primary carbocations, whereas this one is tertiary. It wins. Every other case, only example of resonance being less important. Than hyperconjugation. That's it. Every other case, resonance beats it. So I can say the truth now that I've shown you this one counterexample and the only counterexample that exists, and it's because there's no other way to get two primary carbocations in resonance with each other than the allyl cation. It's kind of like the worst possible resonance, like the most pathetic resonance. So in every other case, resonance dominates. Yes, and Amanda, absolutely. Is the priority of effects the same? Yes, it absolutely is. Nothing has changed because charges are still charges. So we have this resonance thing. It's more important than hyperconjugation, except in this one little side example, which I promise I am not going to use on a test. But now you know. It's pretty useless knowledge, but still, that's okay. Okay, let's take a look at a slightly more complicated example. Don't fuck this up, Trent. No. Sorry, I lied. Oh, I better not mess this up. So I have a symmetrical molecule, which is handy. We're just going to add one equivalent. So don't go just like adding hydrogens willy-nilly. What is the cation you generate? Actually, two questions for you. What is the cation you generate? And what is the most stable resonance structure of that cation? We need more caffeine. Sometimes I think I'm a test candidate for what happens when you drink tons and tons of Splenda in the form of Pepsi Max. I'll either live forever or I'll die at 50. I don't think there's anything in between. Okay, so one thing to note here is the molecule is symmetrical, right? Both double bonds are identical. They're symmetrical. So we don't need to worry about 4 different systems. We only need to worry about 2. So all I'm going to do is I'm going to play with the right-hand double bond. So you play with the left-hand double bond, play around with me playing around with the right-hand double bond. So I have 2 possible products. So which one do you think is more stable? Which one is the one that forms? Those are equivalent statements. Which is more stable, which is the one that forms. Those mean the same thing. Because you only make the more stable one. Three votes for red, 4 votes for red. Positive on tertiary carbon is more stable. Agreed. Second, because of resonance. So Braden coming in with blue. So what Braden has noticed is that you got a resonance structure on the blue one. Okay. Does Team Red want to? Doesn't make any octets, though. I agree. But let's say we compare this guy here with this guy here. What do you think the relative stability of you know, call it purple, blue? Then, yeah, okay. So what do you think the relative stability of purple versus red? Just purple and red. Let's just think about the purple. Like, just pretend that there is no resonance and purple is just a thing on its own. Or compare purple and red. Yeah, okay, they're the same. They're not. We're going to talk a little bit about how they are a little bit different, but they're functionally the same. But blue has got 2 resonance structures, right? So that positive charge is tertiary, but it's not only on tertiary. It's also spread over the secondary. So, you know, in general, this class votes correct. This was the rare example where it didn't. So great job, Braden. You saw the trick. Good catch. Keep an eye out for this because you can form the first carbocation, but then cannot rearrange. Is the expression of the carbocation that you generate the most stable resonance structure for that one? In this case, it wasn't, right? The secondary carbocation, as many of you rightfully noted, is secondary, and it's not as good as a tertiary. But it's in resonance. And it can resonate to a tertiary, and that's pretty awesome. And then that kind of cancels it out, and then this is like gravy stabilization. Okay, so Melitza said, when comparing, I compared it without the H attached and saw resonance with the red. Do we compare? Well, there is no resonance in the red, right? You got, if you, there's no resonance in this intermediate. There's resonance over here, but that's true for both of them. You can't have sort of like H plus, H plus. If the H came off and created a lone pair. Okay, I see your point, Melitza. It doesn't though so much. It's more that we drew it that way to sort of think about how the resonance structure reacts, but it's a lone pair that attacks. You're never going to actually generate a C minus, C plus. You're not going to break the double bond. You're going to break the double bond by attacking an H plus. And so you never see a C minus. Because as soon as the electrons don't go onto the carbon, they kind of like pivot from being carbon-carbon double bond to being carbon-hydrogen. So you never get a C minus. The electrons move from being tied up in double bond to being tied up in a single bond. You now generate a carbocation. We're moving the cation, like the positive charge, from H to carbon. Did it matter which double bond you attack? No, you get the same answer. You get the flip, Lauren, but it would be exactly the same thing. It wouldn't matter. Okay. This is the hard part. Yeah, so you compare the charge species with the H attached. Exactly. You can draw the resonance structure that helps you figure out where you are going to attack the H. Like if it helps you to draw that resonance structure, minus, plus, figure out where you want the plus, where you want the minus. Go ahead, and if that helps you figure out which way the bond is polarized. But it's a model for you to help rationalize which way the bond is polarized. It's not actually a thing. So you're going to compare it with the H attached, like we've been doing so far. This is the hard part. We are basically, all alkene chemistry comes down to this. Where is the charge most stable? That's it. We're going to put a lot of decorations on that. We're going to make it fancy. We're going to show how we can use different reagents to make this happen. But this is the chemistry that drives everything. Everything else is just going to basically build on this. So this whole thing where I said that we're supposed to be talking about the Markovnic combination of water, what the hell is that? Okay, so let's go back to our first example. Actually, we'll go back to Markovnikov's example, which was isoprene. If I take I'm actually going to use his precise example. This is from like, I think it was 1850. So catalytic HCl in water. Okay, as soon as somebody says catalytic HCl, H2SO4, HNO3, phosphoric acid, all I'm thinking is source of H+. Yeah, there's a Cl- there, but there's only a little bit of it. It's not going to do anything. It's catalytic, so it's a source of catalytic H+. So this is equivalent to writing the Cl thingy is just a red herring. If I say one equivalent of HCl, and we're going to see that next class, that's something different, but I'm not. I'm saying there's catalytic amount. Okay. So this is going to be a two-step process. The first step is identify the most reactive thingy in there and react it with something. Yeah, so Melitza, the answer was this, yes. And this is the most stable, and I asked which was the most stable resonance form, it's this one. I like how the anyone, but you can ask me, I'm here for that. Stop me if I go too fast and you need me to go back to a previous question. Yeah. Okay. Try and draw this out to the end. And I can say the water is not innocent here. The water is going to do something. Okay. So let's try this out. First question. What's the most basic thing in this entire system? Everything I've drawn on that arrow. What's the most basic thing? What's going to react to the H+ first? I like how Melitza sees both opportunities and, goes either or. Okay, so is a double bond more reactive than water? Are the electrons in the double bond more accessible than the lone pair on water? What do you think? Yeah, no. So water is the most reactive thing, but it's kind of a trick question. Why is it a trick question? Because all we've done is basically restated the acid as a different thing, but it's just, it doesn't change anything. We're still going to do it with the double bond because this is not stable, and we've done something, and like that's going to now react. It's just something to always keep an eye on. Is sometimes the easiest to do reaction isn't productive. Nothing useful happens. We can kind of ignore it, but it's still good to know what it is, just in case. Okay. So now let's attack our double bond, attacking the hydronium ion, which is what acid does in water, right? Yeah, you can call this an intermediate. I'd be fine if you didn't draw it either. You could just attack the H plus directly with double bond. It's just, you need to know that in water, H plus doesn't exist as like naked H plus, it exists as hydronium. But you cover that in Gen Chem. So hopefully you did your analysis and you go, yeah, tertiary versus primary, this one's easy. No, this funky resonance stuff, straightforward. How do I know that water is more basic? Well, that is a C plus with not everything having its full octet. That is an O plus with everything having its full octet. Which do I prefer? I prefer full octets. Always prefer full octets. Everything having its full octet is the #1 most important thing you can have. So that's why the oxygen is going to be more, the O plus there is more stable because it's a full octet O plus versus a not full octet C plus. But, you know, it can react. It can go backwards. This is reversible, but it can react. Okay. What happens now? Yeah, Amanda, that's exactly it. So Amanda said, is anything that, I'm sorry if I haven't stated this explicitly, is anything that's charged, not the final product, considered an intermediate? Anything that's not the final product is an intermediate. Okay, Noor said add water. Okay, how? Be a bit more specific. You're right. So let's just add a few more, write arrows with words. Or somebody else wants it. There we go. Jesse has it. O lone pair attacks carbocation, add H to pot. Ooh, no, that's wrong. The add H to positive charge is wrong. But O lone pair attacks carbocation, I like that. I think you might have just misstated it, Nor. So we're going to use water to attack the carbocation. So we do that, and we get that. Is that stable? It's definitely better than a carbocation, right? Because now we've gone from a C plus not full octet to an O plus full octet. This is good. No, we don't want a positive charge on oxygen, right? So how do we get rid of that? Yeah, Julia, that's absolutely fine. You can redraw water and draw another arrow. That's fine. I'm just being really lazy. Perfect. There we go, Jesse. Exactly. So Jesse, answer the answer, which is what do you do here? We're going to use another equivalent of water. I'm going to strip away this hydrogen. There's lots of water around, so feel free to use it to grab that. We were seeing that with the carbonyl chemistry. So note, what we've effectively done is we've added an H plus to one side of the double bond, and we've added an OH minus to the other side of the double bond. Or we've added water, right? We have added water across the double bond. So this is why this is an addition of water. Why is this called a Markovnikov addition of water? So I'm going to state the modern interpretation of the Markovnikov definition. There's another one out there. I will state the modern one, I will state the old one, and I'll tell you why the old one is wrong and you should never use it. But it still comes up in textbooks. And I think it might be on Wikipedia, and it is wrong. So a Markovnikov addition reaction is one in which the alkene reacts with an electrophile or as a nucleophile to make the more stable carbocation. So that's what we see here. The alkene reacted with an electrophile. In this case, it was H+. We're going to see lots of other electrophiles, but they're exactly the same. There is nothing different. It's just they're not H+. But who cares? It's the same pattern of reactivity. The alkene reacts with the electrophile to generate the most stable carbocation. And then stuff happens from there. We have another nucleophile come in and attack. But the important part here is you go through the most stable carbocation. This is the modern definition of Markovnikov reaction. The old definition is it actually used to be stated this way: add hydrogen to atom with most hydrogens. So we see that this actually satisfies that old definition. If we compare these two carbons, we added the hydrogen to the bottom carbon, which had the most hydrogens. It had 2. Oh, absolutely. We are going to do more examples of these, Julia. Yeah, we're going to do tons of examples. The problem is that falls apart if you have resonance. It falls apart if you have induction. The only time that's reliable is when only you have to worry about hyperconjugation. And so I don't like that definition. It'll get you the wrong answer. You will never go the wrong way if you make the more stable carbocation. Julia said, can we do more examples of these? Damn straight, we can do some more examples. We can actually even jump ahead a little bit and no, you know what? Let's stick with the same examples. So we have a 6-membered ring. It's been a little while since we had a ring. I'm going to throw you a curveball here. It's not a big curveball. It's like Kitty League curveball, but it's still a curveball. So think about this and try it out. Again, the lone pair on methanol is going to be more reactive, but that's not going to help us. Like, it doesn't do anything. So we're going to attack the double bond. Okay. So hopefully what you've done is you drew an arrow kind of like that. So again, it's important to draw these arrows right? So the arrow is coming. I didn't draw the resonance. You could have drawn a resonance structure and reactive inert. That's perfectly valid too. I'm not going to do that again, unless somebody specifically asks me to sort of analyze resonance structures. I'm drawing the arrow from the middle of that double bond, so I'm indicating it's the electrons in the double bond that are doing the attack, and they're going to the H plus. And hopefully you want my choices between a secondary or a tertiary carbocation. I'm going to make the tertiary carbocation because I don't want to make the secondary one. And now I have a carbocation. I have a methanol nucleophile. That's going to attack the carbocation. Why? Because the carbocation is the most reactive thing there, positive charge thing there. The oxygen lone pair is the most reactive nucleophile. And this is where it comes back to think it's a good idea to think about that in advance, where it didn't help us with the H plus, but it's helping us a lot here. And what we're going to get of course is a positively charged oxygen, and then another equivalent of methanol. I don't think my color changes are actually really doing anything except just, you know, for the sake of it. I guess I do this all in one color. That would be less colorful. And note, I don't need to draw on that hydrogen that I put in there. It's implied, right? So I get this as the product. Cool. Let's do another one. Yeah, the positive charge is on the oxygen. Yes, I'll change the angle on this a little bit more so it's a little bit clearer. Okay. Just want to make us think about now combining another concept in here. Okay, change my atom. Sulfur versus oxygen. What do you think? Big difference? Pretty similar? I have to rethink the entire way of the universe, or do you basically do the same damn thing except now you have sulfur instead of oxygen? Yeah. Yeah, exactly the same thing. Sulfur, oxygen, same row, about the same acidity, same basicity. Yeah, sulfur stabilizes the negative charge a little bit better. Oxygen stabilizes the positive charge a little bit better. We're talking a little bit better, right? It's not going to fundamentally change how this reacts. So if you do this one, now consider the fact that in this top right-hand one here, I didn't draw any stereochemistry at that position. Now, partially it's because it's a meso compound. That's no, it's not a meso compound. It's just achiral, which is fair. This one's not achiral, but even if that one wasn't achiral, I wouldn't be able to draw. It makes no sense. Me saying even if that one wasn't achiral, I wouldn't draw any stereochemistry. I didn't have to consider stereochemistry. You are going to have to consider stereochemistry on this bottom example. So try it out. See if you can give me a product with stereochemistry that you think is going to be the major product. Not the only product, but the major product. Cool. Hopefully hopefully this first arrow is now boring. That'll be good. But it's still scary. Then keep practicing. The assignments are really good for this. There are a lot of examples. Textbook also has a lot of examples. And hopefully you're like, yeah, okay, it's sulfur, it's different, but it's not really that different. So I expect basically the same arrow. So again, I'm drawing from the electrons to the carbocations. Some of you, I'm sure, are thinking, why is he emphasizing this so much? I get it. There are other people who don't get it. Hopefully people watching this in video after the fact. Most of you guys seem pretty engaged. This hopefully is really boring. That's good. Okay, talk to me about the stereochemistry of this sulfur that I just added. Those are not wiggly lines. That's because the electronics on my tablet are shit. There we go. So Nora said, so when we add the sulfur, it'll be behind the plane of view to avoid steric strain. Exactly. So we have this big isopropyl group. It is on the top face. It makes it difficult to get in from the top face because it's there, right? So the sulfur is going to sneak in from the bottom. There's nothing blocking it on the bottom. So preferably our sulfur is going to come in from the bottom. What does that mean for the methyl group at that carbon? Like this methyl group. What's the stereochemistry of that? Gonna have to be top. Exactly, right? Bottom's taken. So we kind of push it top-wise. We don't really care what it wants. We're ignoring it. It didn't get a say in this whole thing. It just got pushed into the position because the sulfur took the other one. I really like the tone in your answer there, Melitza. That's absolutely correct. Okay, so we're not done yet because our sulfur is still charged. So we need to take care of that, but we need to take care of it the same way we've been taking care of charges so far today, which is let's just use another equivalent of the sulfur thingy. Strip this off. This reaction works quite well. It's going to stink. This isopropyl is the stinkiest compound known to man. It actually is. Like I'm not saying that some sort of hyperbole. It is the smelliest thing out there. It is absolutely disgusting and foul. We have a bottle of it in a freezer in our lab, and it's inside like 4 other containers, and the freezer still stinks a lot when you open it. Kind of like evacuate the building if a little drop of it lands somewhere. It's not dangerous. It's not toxic. It smells awful. Did my lab catch fire? I have no comment on that. But I can say that there was a fire in Essex Hall, and it was due to a faulty electrical circuit that blew overnight. because of the electrical charges, that surge that went off across and went across Windsor because everything was down. It was just, wasn't Essex Hall's fault for once, which was nice. Anyways, there. We have a product. So I can say it gets harder from here, but it doesn't really. What we're going to be doing is we're going to go through some different examples. There's some tricks and things, but really what we're trying to keep our eye on here is where does the charges want to be? What makes the charges more stable? And we saw the other component here, which was sterics. So where do things want to approach from? Because what makes the orientation and conformations more stable? And that's it. Like literally, that is chemistry. That is all there is to it. Everything we've been doing to this point is kind of leading us to this discussion of how do we keep charges most stable to make things react, and things are going to react to minimize charges, and how do we get things to avoid other things, and that's sterics. And sterics and electronics. Electronics is charges, and sterics is like clouds of electrons blocking things. That's all there is. So you're confused where the other part of the sulfur went after the second intermediate to the final. Oh. So the sulfur is still here. Like all this is still attached. It's right here. So the sulfur thing is still here. All we did was we lose the hydrogen. We have another molecule that's grabbing that hydrogen. I can draw it in. It's not wrong to. I just don't bother because it's not my major organic component and I don't care. Like we're not balancing the equations. Did that help? Yeah, okay. Yeah, it's still there. Okay, cool. Awesome. We're at 2:30. We're actually a little bit ahead. Because we're going to talk about more of this next time. So we're going to talk about Markovnikov additions of bromine tomorrow. Yeah, the other H is still attached. I just stopped drawing it because it's implied, right? I can draw it or not, and it means the same thing. I drew it in initially because it's like, hey, I want to show where the H is, and that's kind of important. But this means carbon with the hydrogen attached. Well, it means actually carbon with two hydrogens attached, one of which I've drawn explicitly. This means the same thing. Well, it's not random. That's a really good question, Katie. So we're trying to wrestle not undergrads, we're trying to wrestle grad students, which is actually harder. And so we hope to be doing all the marking next week. So everyone got their schedule cleared and we can get that done. So hopefully we're going to get the marking all done next week. So I'm optimistic I'll be able to get you grades back by a week today. Maybe sooner than that, but everyone's exhausted. I don't want to break the grad students. So again, what I always do this, and I think I've stated explicitly, and I'll state it explicitly again. The midterm is essentially an insurance practice thing. If you do better on the final, your midterm mark disappears. So if it takes a while for stuff to click, that's cool. But the midterm here actually kind of fit nicely right before we really started chemistry, right? It was like all the midterm was on all the preliminary stuff. And now we're applying all that stuff to chemistry. So it's going to break nicely. Like none of those concepts are going, like the final is cumulative, but I'll probably be testing all those previous concepts in the context of the chemistry that we're doing, because I can basically tweak them all in. I can still ask some questions about it too, but what if you do better on the midterm, you don't get to replace the final with the midterm? I'm actually kind of upset because, to be honest, I think the midterm was easy. And so what I mean by that is I'll see what the grades come back with. And so maybe a lot of you thought, hey, that wasn't that bad. And if you did, you probably did really, really well. So we'll see how this comes back. I'm kind of suspecting my average isn't going to be any better this year than it ever is. But I kind of always like it when the midterm puts the fear of God in people, because maybe for some people that's sort of the thing that we need, and I'm not sure this one did. Yeah, so the carbonyl one, I don't have answers up yet. I will put some up. It's a thing I need to do. I'll try and get to that next week when my GAs are grading. That's it. Like, Faith, my goal is that all these concepts make sense the morning you wake up for the final exam. I know somebody who has one of their kids is in the class, and he was letting me know that his child was fucking terrified for the course. And I went, okay, I'm doing my job then. There should be the right amount of fear. Well, we're going to come back to the carbonyls, and hopefully it's going to make more sense. So we'll start here, and maybe when we get back to it, go, oh, I don't know why I was confused about this at all. But it's okay that you are right now. It's absolutely fine, and that doesn't mean that you're stupid. It doesn't mean that you're slow. It doesn't mean that you're off pace. This stuff is hard, and I do not know what order to teach this in, and we're trying stuff out. I promise you that almost everybody who's putting any effort into this, okay, not any effort, but an appropriate amount of effort into this will be fine, and it'll all more or less make sense by the final. But it all doesn't really come together until everything's there, and I haven't yet figured out how to plug plugs into your brains and get multiple channels in parallel and information coming in. Yeah, Sarah. So yeah, Alyssa, that is what I mean. Now, can you assign RNS to that? Absolutely, you can assign RNS to that. I'm not going to do it right now. It's fully possible to do. Oh, Amanda, yeah, you can just come to office hours and ask me anything. That's what they're for. You can also do that kind of in this thing going, I just don't understand X, as long as it's more or less on what we're talking, kind of on train with where we are in the schedule. There's some wiggle room near the end, so we can always revise some stuff too. Julia says, what am I doing in my lab? So I'm going to put the caveat in, I'm not taking any more second year students in my lab because we're a little oversubscribed with second year students. So I'm looking for first years, and none of you guys are in first year. I make drugs, that's what I do. And new drugs for diseases, somebody around the world identifies an interesting protein, and I go, ooh, nobody's made a drug against that. I'm going to make a drug against that. And I make diagnostic probes so we can identify new types of cancer a little bit faster. And I make sort of delivery nanorobots so I can get the drugs I make into the right cells so they don't go to the wrong cells. They only go to cancer cells. And hopefully, we can package all fancy ass chemotherapeutics in there, and suddenly, people on chemotherapies aren't losing their hair and their fingers and their bones aren't falling apart and their immune systems aren't collapsing. So I'm interested in trying to design new drugs and get them to the right cells. But in general, what I'm really interested in is using design principles to figure out things I want to make, and then I want to make them, and I want to make up new chemistry, because often we're trying to make bonds that don't exist and structures that don't exist, so we need to figure out new ways to do that. And then I like testing them, doing biology, because I like closing the circle. And then once we can test them and see what they do, then we realize that they kind of suck, and we need to go back and design something new. And so basically I just spend all my time running around in circles, from designing new things, making new things, testing things, realizing it's not good enough, redesigning. So I just run around in circles. Yeah, that's what I do, Julia, in short. Okay, everyone, we're done. You guys have labs and courses and fun things to do. Enjoy your weekend. Yeah, take care. I think ChemDraw is working. I hopefully fixed that. I don't know for sure, but none of my students in my lab have been complaining about ChemDraw Prime more than they complain about ChemDraw Prime, but no one's been complaining about it. I think it's working. I think you'd be able to download it, Ashley.